TTL Computer 2. Today we'll be taking a look at some updates to our memory map. And we'll just get right into this now. A memory map does exactly what it says it does. It maps our address space of our computer to specific devices or purposes. And you can see that we have a 64K address space, since we have a 16-bit address, and address from hex 0 to 1 FFF is going to be our onboard ROM, which is 8K ROM. Hex address 2000 through 3 FFF is going to be for our devices. Hex 4000 through 7 FFF is going to be for our future memory expansion, and hex address 8000 through FFFF is our onboard RAM, and the last 256 bytes of that is our stack space. Now, I've shared this before on the community pages, but what I've added now is I've added this expansion of the address to a bitwise expansion, right? So we have our address bit A0 through A15, and then I have this little value indicators for the bits, just as a little cheat sheet. So, this is the low nibble and the high nibble of the first byte, and the low nibble and the high nibble of the high byte of the address, right? And this bit is 0x01, 0x02, 04, 08, and this is X10, X20, X40, and X80, right? And the same thing for the high order byte. So I just want to represent these the memory addresses in bit patterns, and I did that for a specific reason. But we can see that we have the bit patterns here, right? 000 through 1FFF. This is 1, and then FFF, right, for each of the memory map areas. Now, the reason why I did that is because, all right, so all of our devices are all connected to the same 16-bit address bus, and so they're all also connected to the same 8-bit data bus. So how do the devices or the chips know that they should be reacting to what's on the address in the data bus? And it does that by special circuitry that we call decode circuitry. So the decode circuitry looks at the address that's being published on the address bus, and if it recognizes that address, it will enable the device, right, that it should for that memory address. So what I've done here is, so after we've blown this out with all the bit patterns, I've really just noted here which bits the decode logic will look at to determine if this device should be, active for this address, for the memory address that's on the bus. And for our onboard RAM, since this is the top 32 bits of our 32K bytes of our 64K byte memory space, it just has to look at this high order bit. If bit A15 is a 1, then our RAM chip is enabled. For our expanded RAM, if A15 is 0 and A14 is 1, that means the expanded RAM chip is active. For all of our memory map devices, if bit A15 and 14 are 0 and bit 13 is 1, then our memory map devices would be active. And for our onboard ROM, if bits A15 and 14 and 13 are all 0, then our onboard ROM is active, right? And I'm called out these patterns here that we just walked through. Okay, so that just overall shows us the highest view, I guess. But we need to look at the devices further, because we have multiple devices mapped in here. All these others are just this is just a 32K RAM chip. This is an 8K ROM chip. but we have, and this would be probably a 16K RAM chip. But the ROM devices, we have multiple devices mapped here. So we're kind of looking at a detail of that now, right? We have address 2000, all the way to 3FFF. But so before the changes I've made right now, we had our hex display and our monitor and our keyboard. We had them mapped to 2001 and 2002 and 2004, right? So it was this same pattern, 1, 2, and 4, but shifted over to here, right? So what I did right now is I've shifted them up from the low nibble to the high nibble. So we still have the 1, 2, and 4, but it's 2010 and 2020 and 2040. So I shifted those up to the high nibble. Now, what really started this whole exercise was how we were going to map in our 16550 serial UART. And that serial UART is controlled by the computer using eight eight control registers are provided by the UART, and those need to be mapped into our address space so that we can read and write to them. So we're going to use, right, following the same pattern, 2010, 20, 40, right? We're up to bit A7, right, which is 2080, which is going to be where our UART is going to be mapped in. Now, this is why I pushed these up to the high nibble, because we need these low order bits in the low nibble to signify which register we're going to be mapped into. So 000 is register 1 in the UART. 1 is right, register 1, register 2, register 3, register 4, register 5, register 6, and register 7 in our UART, right? And those are going to be mapped in at address 2080, 2081, 82, 83, 84, 85, 86, and 87. So that's how we are going to read and write to our serial UART chip. Now, in our prior slide, I said that the devices only had to look at the top 3 bits of the address, right? A 14, 15, and 13. And that's partly true. But now you can see that we're looking at 4 bits here. So here's the top 3 bits, but our decode logic is also going to have to consider this. So it's going to use the top 4 bits, because this will be the devices in the 2000 range. And then down here, where the bit is 1, this will start the devices for the 3000 range devices. But this is, so we've mapped the 2000 range kind of using this approach. The 3000 range might be different. I don't know. We don't have any use for them now. We're going to leave it. It's really a clean slate for future use, but it won't necessarily use the same pattern that we used here. Now, so I've called out the decoding again. So what we're doing here is called, we're doing a partial address decode. We're not doing a full address decode for our devices, right? If we were using a full address decode, our decode logic would have to look at all 16 bits of the memory address to determine if this device is active. But we're not doing that. We're shortcutting it, right? We're only going to look at 5 bits, these 4 and this 1. So we're not looking at all of them. And that could be problematic if other addresses are sent, because if this device is only looking at these bits, if an address data is sent to these addresses, the hex device would react to it. And that's not something we want to do. So what we're doing with this partial decode is we are simplifying our decode circuitry, just because we want to. And we're kind of doing this with our eyes open. We know that we are never going to send this data, with these bits active here to these devices. We know we're not going to do that because we're only ever going to send, these bit patterns for these high order addresses. So it's just something that we do to, again, simplify our circuitry, but we do it with our eyes open, and we realize we have that limitation. So let's look over to our digital simulation, and we can take a look at how this might be used or manifested. Okay, so I am going to start our simulation. We see our hex display is 0 right now. I'm going to start this up, let that run a bit, and then I'm going to stop this. Okay, so we let this run, and we can see that our hex address now is updated to FF. So what I've done is written a small memory check program, and this can run through any range in memory. And what it does is it attempts to write FF to that memory address location and read from that memory location, and then go on to the next memory location. So we see that here it's starting at 2000, and you're not seeing anything, but so this program wrote FF to address 2000, then it went to 2001 and wrote FF to there. And so now we can see this is going down, and where we go to 2010, right? So here is where it wrote the FF to address 2010, which updated our hex display. So we're going on, right? And nothing else is mapped into these other addresses. So now we get to address 2020, right? And that is our monitor. And this is the monitor here. We're looking at it. So we're at address 2020, and this program now wrote FF to the monitor. And we see that here. This umlaut Y thing is the FF written to the monitor. And then it goes on to, the next memory address, 2021. And it's writing FF again. And now you see we have that umlaut again. So this is kind of showing us, this is a manifestation of the partial decode logic that we did in our devices, right? So it mapped in the 2020 here, but now it's also mapping in the 2021, is also writing to the monitor, and 22 and 23, and on the whole series of, right, all the way up to 2040. Now we've got to our keyboard address, and now you see the umlauts are gone because it's not doing anything with that with the FF. But that just goes to show you how we can take a shortcut, and we can skinny down our decode logic, in our devices to simplify our build. But we need to be, we need to do that with our eyes open and realize that if we get address combinations that we are not anticipating, we may, accidentally, write to devices that we don't really intend to write to. Okay, so that's so I wrote this memory program, and I really use this to run through our whole memory address space from 00 to FFFF, and I kind of got some results that I didn't anticipate. So that was a purposeful exercise I went through, but that was an early run with the memory map that I had and the decode logic. But that's been adjusted and shored up for what we need it to be. But so again, so this was just a little bit of a look at our the details of our decode, our device decode logic, specifically really for our serial UART that we're going to be adding. But to accommodate this and the use of these low order, bits 0, 1, and 2 as the address bits for the serial UART, we had to shift up what we had been using as the lower nibble to the upper nibble for our devices. So our devices are now going to be 2010, 2020, 2040, and 2080 for our serial UART. So that's it for today. I did get the boards back from JLC PCB for our registers card, and I've started populating that, and that should be done in the next day or two. So until next time, that's it. Thanks for watching.